In this video, we're going to introduce the concepts of work and energy. And we're also going to show how that formulation of the physics is equivalent to the previous formulations we had in terms of the kinematic equations and Newton's second law. So to begin with, to try to conceptually think about what work is telling us, let's consider we have some block on a flat surface, and we're going to apply some force, we'll say Fa, down at an angle of theta. And we'd like to move this block some distance d. Previously, we had some kinematic equations that we could use to describe the situation. But as this block moves, that leads us to our definition of work. The work done on an object by a force over some distance is defined to be that force times the distance traveled times the cosine of the angle between the force and that distance. This can also be written in another way, and that's to say that the work done by this force is equal to the force that's parallel to the distance times the distance. As we've seen before when we did free body diagrams, an object can have multiple forces acting on it. And so when we want to talk about the work done on an object, we want to be able to talk about the total work done on the object by all of the forces that are acting on it. So that's to say that the total work is going to be equal to the sum of the individual works done by each force. Now, when we write the sum of the total work, we can say that this is going to be equal to the change in what's called the kinetic energy, where the kinetic energy is defined to be 1/2 mv squared. So let's go back to our example where we had this block on the surface and we're pushing it along. We know from our kinematic equations and the way that we've described things before that as we're applying this force, this block's going to accelerate, so it's going to have a different velocity initially and a different velocity at the end. And so what we're saying here when we're formulating this in terms of the work-energy theorem is to say that if we add all of the work acting on this object, that's going to be equal to the difference between the kinetic energy at the end of its motion, or when it gets to the distance d, and when it starts. So it's going to move over, and we can take the difference between the kinetic energy at the end and the beginning, and that's going to be equal to the total work acting on the object. So what we'd like to do now is prove analytically how our new formulation in terms of the work-energy theorem is equivalent to our previous formulation in terms of kinematic equations. So to start with, what I'd like to do is write down what the work-energy theorem says. And that says that the work, or the total work, acting on an object is going to be equal to the change in kinetic energy, where the change in kinetic energy is going to be the difference in the final kinetic energy. So 1/2 mvf squared minus 1/2 mvi squared. Okay. We also know from the definition of the work that the total work can be written as the total force times the distance that this force acts over times the cosine of the angle between them. Now, for this example, let's consider a block that we're going to push with some force. And we're going to move just in one dimension. So this is going to be the distance d. And this is the only force that's acting parallel to the direction of motion. And it's exactly parallel to the direction of motion. Which is to say then that this cosine of theta is just going to be 1, because the distance that I'm traveling, or the direction that distance is the same direction as the direction of the force. So what we can also say from Newton's second law is that the sum of the forces is equal to the mass times acceleration, which is to say that the total force is equal to the mass times acceleration. So what I can actually do in this equation is replace this to say that the mass times acceleration times the distance is going to be equal to the total work. Now let's put these two lines together to say that 1/2 mvf squared minus 1/2 mvi squared is going to be equal to ma times d. Okay. Now let's kind of play around with this to rearrange it. So one thing that I noticed immediately is that I have masses common to everything here, so I can cancel those out. And let's also move a factor of 1/2 over to this side. So multiply the entire equation by 2. So we have vf squared minus vi squared is going to be equal to 2a times the distance. And to get this exactly in the form that we had for our kinematic equations, we're just going to move the initial velocity over to the other side. And so that's to say Vf squared is going to be equal to Vi squared plus 2AD. And this equation should be familiar to you. This is actually one of the kinematic equations that we listed before. And so in going through this process, what we were able to show is that by using the work-energy theorem, we can recover the same equation that we had by using kinematics. And this is something that's really important in physics. If you introduce a new idea, it needs to recover the same results as the old idea. Great. So now we understand the kinetic energy and how work can impart kinetic energy. And we've also seen how the formulation of the work-energy theorem is equivalent to the formulation in terms of kinematics. But that's actually not the whole story. So in order to get the whole story, consider the following example. Consider we have some block of mass m resting on the ground. And we know that it's going to have the force of gravity acting on it. This is just going to be mg pointing down. We'd like this block to be lifted a height of h so that it undergoes this motion. So what we can see is that according to the work-energy theorem, we can calculate what the work done by gravity is. This is going to be the force of gravity times the distance that this block moves times the cosine of the angle between them. Okay. So when we do this calculation, we end up seeing that this is going to be minus mgh because the block is going to be moving in a direction opposite of the direction that the force is pointing. And as we look at this block, now that it's lifted up here, what we say is it has the potential to be able to fall, to create kinetic energy. So what we do is we define the potential energy as this tendency or this ability of an object to do work. So now that we've kind of conceptually defined potential energy, let's go ahead and talk about it in more of an algebraic way. So here are some examples of potential energy. We can talk about the gravitational potential energy as U sub g is equal to mgh, the height that it might be above the ground. We could also talk about the spring potential energy. So if we have a spring, we can compress the spring. And so the spring potential energy, U sub s, is going to be 1/2 k, which is the spring constant, times the distance that we've compressed it, squared. In general, for conservative forces, what we can say is that work done by a conservative force is going to be equal to the negative change in potential energy. So let's build off our discussions of potential energy, kinetic energy, and the work-energy theorem to derive what's called conservation of energy. So to start with, what we'll do is we'll write down the work-energy theorem. So the work done on an object, if it's the total work, is going to be equal to the change in kinetic energy. We also saw from our last slide, our discussion of the potential energy, that if these are conservative forces acting on this object, that this can also be written as the negative change in potential energy. So let's go ahead and expand this change in kinetic energy and this change in potential energy and see if we can rearrange it in a way that's advantageous. So what we can do is we can say that the final kinetic energy minus the initial kinetic energy is going to be equal to the negative times the final potential energy minus the initial potential energy. So let's rearrange this so that we have all the finals on one side and all the initials on the other side. And so when we do that, what we end up seeing is the initial kinetic energy plus the initial potential energy is going to be equal to the final kinetic energy plus the final potential energy. Now, this sum of energy that I have here, I have kinetic energy and potential energy, we just call the total energy. And when we define the total energy, we just call that E. So what I'm going to say is this term right here, I'm going to say this is E initial, is going to be equal to this term right here, which is what I call E final. And what I have written here now is what's called conservation of energy. This says that the energy in the initial state is equal to the energy in the final state. And so what's really interesting about this, and something we might have noticed in our discussions of work and energy, is that there's no vectors associated with this. This is just, if I had some point here, call this the initial point, and I had some point here, the final point, the energy here at the initial point is equal to the energy here at the final point, provided that we're only dealing with conservative forces. So to this point, you've heard me talk about conservative and non-conservative forces. And now we really want to define what the difference is between them. And this really gets down to whether energy is conserved or not. That's really what the conservative force cares about, is whether or not the energy is conserved. And so conservative forces, some examples of conservative forces are the gravitational force and the spring force. Examples of non-conservative forces are friction and tension. And so what you can do for conservative forces, you can define the potential energy for them. You can't define some potential energy for a non-conservative force. Ultimately, this is due to the fact that conservative forces don't care about the path that I take between one point and another point, but non-conservative forces do. And ultimately, energy is only conserved when a conservative force acts on an object, but not when a non-conservative force acts on the object. So what can we do to modify the way that we've written conservation of energy to incorporate non-conservative forces? If you have non-conservative forces, of course, energy is not conserved, but you can still kind of play around with the work-energy theorem in order to get an equation that still is useful for our calculations. And so what we can do is we can start by writing the work-energy theorem. So that's to say that the total work is going to be equal to the change in kinetic energy. And so this total work here can actually be split apart and written in terms of both the non-conservative work and the conservative work. So we can say that this is two pieces now, the work done by the conservative forces and the work done by the non-conservative forces. And we can add these together. This is equal to the change in kinetic energy. Now, because conservative forces can have some potential energy associated with them, what we can do is we can write this term as the negative change in potential energy. And so the negative change in potential energy plus the work done by non-conservative forces is going to be equal to the change in kinetic energy. Now, to get this to talk about energy, what we want is we want some combination of the kinetic energy and the potential energy. So if we move the potential energy to the right side of the equation, what we have is the work done by non-conservative forces is going to be equal to the change in kinetic energy plus the change in potential energy. But the change in potential energy plus the change in kinetic energy can be written as the change in the total energy. And so what we have in the end is that the work done by non-conservative forces is going to be equal to the change in the energy. Now let's now we've attained this equation, let's see what it means. So say I have some point here, we call this point 1. And we have another point here, call this point 2. We can define what the energy is at point 1 and the energy at point 2. So this would be E1 and this would be E2. But we have to take some path to get from E1 to E2. It could be any path. We can have some wiggly line here. And as we're going from this point where I'm finding E1 to this point where I'm finding E2, there's going to be some work done by some non-conservative forces in between here. So this is the work done by the non-conservative force. And so this is really what this equation is saying. Define the energy at these two states. And then the difference in the energy between the final state and the initial state is going to be equal to the work done by the non-conservative forces between these two states. In this video, we defined what's called the work-energy theorem. In doing so, we demonstrated how this is equivalent to our previous formulations of the physics in terms of kinematics and Newton's second law. Additionally, we showed how conservation of energy can be derived and the difference between conservative and non-conservative forces and works. In the next video, Professor Shepard will be demonstrating the use of these new principles to solve two different problems. Thank you.